about that. Okay, 11 chapter for exam. Okay, the first one you can, okay, even though the introductions, but it will provide some necessary information. Okay, we will go, okay, we will review them briefly. Okay. Today, the engineering graduate is no longer employers solely for the technical design aspect of the engineering problems, the air water pollution, the urban planning, the mass transportation, and the discovery of the new energy source, the the conversion of the existing natural resource. Okay, this why, okay, some of you may have the questions why you must study theoretical engineering, okay, theoretical circuit, because the circuit today you can see that almost everything require theoretical power. Okay, even though today is one of the biggest, okay, one of the news biggest automobile is Tesla. Okay, you can see that the Tesla provide about the automobile that drive by the battery only. Therefore, all design is based on theoretical circuit designing. Okay, no longer use the combustion engine. I don't told that, okay, the combustion engine is already obsolete and die out. No, it will be used in truck or the others, okay, transportation. But for the about the personal car, it will be reduced of using the combustion engine and the gasoline. Okay. And another one's topic in this is about how to create the battery. Okay, the battery that for the Tesla or the battery for the mobile phone include in the airplane. Okay, is one of the main energies for that automobiles or the airplane. Okay, you can see that. Okay, that's why you must know about the theoretical topics. At least, okay, you not just to be the expert on the theoretical field, but at least you must know about the idea of them, how to design them roughly. Okay, when you see the cable wire or so on, you will know about the blueprint. You see the blueprint, you will know this is a theoretical circuit designing. Okay, in the almost okay. Okay, for another one is used in the discovery of the new energy source. You can see that we use in the batteries. Okay, so 4 topics. Okay, the mass transportation. The mass transportation, you can see that today the mass transportation is not car, not the airplane. It used train, especially in theoretical train. Okay, due to it can reduce about the pollution. Okay, you can see that today the Bangkok have the problem about the not only the COVID. Okay, it have the problem in the particle. Okay, almost all main field. Okay, you can see that the air and the water pollution. The pollution is came from one of the main pollution, the particles. Okay, 2.5 ppm, or it came from combustion engine, the truck, the automobile of the trucks. Okay, is okay. I think is the benzene engine will be released a few, but the diesel, yes, is have a lot of problem. Okay, the next one is the conversion of the existing natural resource. Okay, now after you know about this idea roughly, okay, next step we go to contribute to the solution of this engineering problem, and engineering must acquire many skills. Okay, and almost all skill is already provide you as the general subjects, okay, in the first year, such as the circuit, okay, maybe the second year, okay, the circuit, the mechanic, the material, okay, the chemistry, and so on. Okay, we use, okay, therefore the school will provide this as the fundamental subjects or the primary subjects already. Okay, the fundamental subject of this tech is, okay, the linear circuit analysis. Anyone, excuse me, do you already have the book already or don't have it?
Yes, John, we have the book.
All right.
Yeah, we have it. But which edition, Achan, this semester?
Okay. All right. It's okay. Okay. Therefore, is if you have the books, okay, you can follow them. Okay. All of you have it, right? Okay.
Yes.
Okay, this slide, okay, you can you maybe open the books, okay, maybe PDF or maybe in the hard copy, okay, for a while. Everything in the slide is already in the textbook. You only mark them, okay? But don't worry about this chapter. This chapter is not exist in the midterm and the final directly. But at least I will provide that because it will give you about the idea why you must study about this. Okay. Almost all topic in this textbook is the linear, but in the real case, okay, the real case is almost all is a non-linear. You may have the questions why you must study the linear, because we can approximate non-linear to be linear, okay, for the easy in the computation, okay, even though we may be lost some accuracies, okay, a great many systems behave in a reasonably linear fashion over a limit range, allow us to model them as the linear system if we keep the range limitation in mind, okay. For example, during you study in the kangaroos, you can see that we have the curve, okay. If you cut them in the small piece, okay, of the curve, okay, you will tell them the curve will be a straight line, okay. The same idea, okay. We cut them, okay. Therefore, in the circuits, we assume them to be linear first, okay. The linear problem are inherently more easy to solve, okay, than the non-linear counterpart, okay. For this topic, we separate them into the four, okay? The DC analysis, okay? The DC analysis comprise of the chapter 1 to chapter 5, okay? The midterm section, okay? The transients analysis is about the chapter 7, 8, and 9, okay? Chapters, yes. 6 is, we discussed that, okay? 6 is about the op-amp, okay? We concentrate on 7, 8, and 9, okay? And for the frequency response or the AC analysis, another 3 chapters after that, okay? 10, 11, and the 12, okay? Okay, for the time domain and the frequencies domain analysis of these subjects leads directly into the discussion of the signal processing. We use them in the signal processing, power transmission, control theory, and the communication. Okay. The engineering take a fundamental understand of the scientific principle, combine this with a practical knowledge often expressed in the mathematical term and arrive at the solution to the given problem. Okay. The core of the analysis is mean if, okay, the analysis is a process to which we determine the scope of the problem, obtain these information required to understand it, and compute the parameter of interest. For example, the analysis, the problem of the analysis you frequently found in the engineering school, okay. For example, in the mechanics, the circuit, okay, or the electronics subjects, okay, the instructor will be provide you or give you a circuit, okay, diagram, okay, and ask you the voltage at some point, the current at some point, okay. This thing we call analysis, okay. You know the circuit, you would like, or you know about the mechanics diagram, okay. You would like to find some force at some point, you would like to find the current at some point, the voltage at some point, okay. But a few subject in the bachelor degree is based on the designing. The design is a process by which we synthesize some things new as a part of the solution to the problem. The designing is frequently found in maybe the 4th year subjects, especially in the senior projects, okay? When you would like to design something, okay, to solve some problem. For example, you decide the robot walking to solve about, to seek the track, okay, to rescue the problem or so on, okay? It is called the designing, okay? The computer aids analysis, solving this type of the equation that result from the circuit analysis can often become notably cumbersome for even moderate complex circuit. What about this meaning? Is meaning even though today, you can see that you have the big computers, okay? The computers may be laptop or notebook, okay? Or maybe the supercomputer is very fast one, okay? But some problems for solving in the real world is still have you cannot solve them yet, okay? For example, you would like to solve 3 equations, 3 unknown, okay? By the linear program, you can use your calculator to solve them. But if you would like to solve them, 50 equation, 50 unknown, the way to solve is not easy. In the real world, in the real problem in the world, sometimes you must use the supercomputer to determine the solution of that. Okay. Therefore, in the engineering, we have the computer-aided analysis is a powerful tool. Therefore, it allows us to vary the parameters value and evaluate the change in the circuit performance and to consider the several variations to designing in the straightforward manner. Yeah. This thing is, okay, the example in the books, okay, is about the carburetor, but the performance of them is lower than the carburetors, okay, is, okay, it's about the differential engines, okay, that is already in the museums already, okay. This is the more powerful, is about the, okay, the electric circuit simulation program, okay. You can see that in this program as an amplifier circuit draw using the commercial schematics capture software packages. Yeah, it's an op amp. Okay, you can push, you can vary the voltage in here, and you can measure what about the output is. Okay, you decide them, every circuit you decide them in this software first. Okay, and after it can generate, okay, the desirable output. Okay, you will buy the real equipment, connect them, follow this diagram. Okay, and you measure them. Okay, the real one maybe have a little different from this simulation, but the overall output will be in the same manner. Okay. Okay. The way of thinking is about, this is a chart for the thinking to solve the problem in the engineering, not only my subjects, but can use for the other. When you read the problems, okay, you extract that how many information you get. For example, okay, when you would like to solve, okay, the instructor would like to ask you about the Ohm's law. Okay, V equal to IR. Okay, the questions, okay, if it asks you for V, you know that you can find V if you know I and if you know R. Okay, but in some case, the questions don't give you I directly. Okay, you must extract I or compute I from somewhere in the circuit. Okay, you're checking first. Okay, the necessary parameter is already enough or not. If it's enough, you can compute that. Okay, you know I, you know R, you can find V immediately. But if it's not, you will try to get I or R from the other point or the other location in the schematics. Okay, to tracking them or from the other situation. Okay, to tracking that. Okay, in order to get the enough parameter. Okay, after you get I and after you get R, you can get V easily. Okay, V equal to IR, and you can compute that. The same, for example, if you have three equations, you know that, okay, if you have three unknown, you know that you must create up to three equations to solve them. Three equations for solve three unknown. But if you have three unknown, but you have two equations, okay, you know that you must try to find or construct another one equation that relates the first three unknown. Okay, if you can create them, okay, you can solve them. But if you cannot create, you cannot solve them yet. Okay, until you can find. But fortunately that in the real world, sometimes you cannot find the third equation easily. But in the problem, in the midterm or in the final, it's guaranteed that you can find them from somewhere or some point in the question. Okay, it's about here, about the idea of the, okay, about the first introduction of the chapter 1. Okay, we go to the chapter 2. Wait a minute. Yeah, can you see that, the chapter 2?
Yes.
Yes, yes.
Okay, the chapter 2 is teach you about to know and how to apply, okay, the Kirchhoff current law and the Kirchhoff, the Ohm's law. Oh, sorry, to apply the Ohm's law and some basic equipment first, okay, or the definition. Okay, the primary topics of this text is the analysis of the electrical circuit and the system. It means that, okay, the almost all problem in this textbook will be provide you the circuit schematic, okay, and ask you the voltage at some point, the current at some point, or the power at some point. Is in the circuit, it have only four quantity that we frequently ask you, okay, the current, the voltage. If you know the current, you know the voltage, okay, you can find the power, okay, P equal to IV, okay, and if you integrate the power respect to time, you get energy. Therefore, it have about four main quantity that frequently asks you. Okay, but the current and the voltage It depends on which point that the question asks. Okay, it may be ask you the current at that resistor, the current at those resistor, the voltage at that resistor, the voltage at those resistor, and what about the power that the resistor consume or generate, or so on. Okay, next one, the conducting. Okay, in conducting a particular analysis, we often find ourselves seeking a specific here, the current, the voltage, and the power. Unit of the current is ampere. Unit of the voltage is volt, and the units of the power is watt. Okay, and if you integrate the power, it gives you the energy. Okay, the unit of the energy is joule. Okay, so we begin with the brief descriptions of this quantity. Okay, okay, the voltage, when you define the voltage, it must be have plus and minus sign clearly. Okay, okay. And if you define the current, you must have the arrow direction, okay, clearly. Okay, we often make the difference between wrong and the right answer by you confuse or press plus and minus, or the directions arrow will be wrong. Okay, be careful about that. Okay, even though it's the first step, but it's the most important step in the analysis. Okay. Okay, next one. Okay, before we go to the define about the quality of them. Okay, we teach you about the unit of them first. Okay, the value of some measurable quantity. In the engineering, we frequently write the unit and the number in this form. Okay, and the unit that we frequently use in the world is the SI unit, or the International System of the Unit. It came from the General Conference on the Weight and the Measurement in the 1960, maybe about the 60 or 20 years before. Okay, the idea of them at that time. Okay, it will be defined. This will be defined only some necessary quantities. Okay, the range, unit of the range is meter. Okay, unit of the mass is kilogram. Okay, kg. Okay, unit of the time is second. Remember that unit of the time is not year. Okay, not minute. Okay, you must change them to be second first before you compute that. The current, unit of the current is the ampere. Okay, unit of the temperature. The temperature in the engineering not Celsius. It uses the Kelvin. Okay, and the unit of the amount of the substance is the mole. Okay, the luminous intensity. Okay, intensity is the candela. Okay, this unit you will refine them again when you study in the illumination designing. Okay, the illumination designing is mean, okay, for example, in the buildings. Okay, for example, in your maybe in the lecture room. Okay, you can see that when you turn on the light. Okay, is the light is constantly in the high intensity. Okay, it seems every, okay, you can read or you can write the textbook very clearly. Okay, but in the hallway, okay, in the walkway, okay, the illumination of the ramp will be a little bit lower than in the room, because in the designing, we don't expect that anyone read the book in the hallway, but the objective to have the light in the hallway is mean you can see some barricade, okay, that you don't flip, okay, or don't fall in the hallway. Okay, next one is the work and the energies. Okay, the work and the energy is unit of them is a joule. Okay, the last one is the watt. Okay, the power of them is a watt. Okay, you can see that the main quantity that we frequently ask is about the current, the voltage, the power, and the energies. Okay, unit of them is, okay, the current is ampere, the voltage is a volt, and the power is a watt. You integrate power, give you energy. Okay, the SI unit use the decimal system to relate the largest and the smallest unit to the basic unit, and employ prefix to signify the various power of 10. Okay, if the unit is so big, okay, you can see that if the unit is so big, okay, for example, 10,000, 20,000, okay, it's difficult to write, okay, because it has so many zeros, okay, it have a high chance for error. Therefore, in the engineering, okay, we use the prefix to prevent this situation, okay, and the number that we write them will be between 1 to 999, okay. Okay, here this, okay, for example, okay, What about your HUD? Okay, I think everyone already have the computers now. Okay, your hard disk may be 2 terabyte, right? 2 terabyte. What about the size of them? Terabyte is here. Okay, you can see that. Okay, some maybe have a very small, for example, 500 gigabyte. Okay, 500 gigabyte is here. You can see that why the number is still 500. Okay, why we don't tell them, okay, it have 0.5 terabyte? No, in the engineering, okay, the number will be between 0, 1 and 999. If it equal to 0.5, no, we change them to be 500 gigabyte instead. Instead, we told them 0.5 terabyte is not, okay, and so on. Okay, you can see that the units that almost all units you frequently use in your life, but you never known about that. Or another one is, for example, okay, what about your CPU speed? Okay, the CPUs that speed up, okay, the core CPU maybe the okay, AMD or the Intel maybe 2.4 gigahertz, right? Giga is here, okay, gigahertz, okay, 2.4. You can see that. We don't say that, okay, your frequencies, okay, for your CPU is 2050, 2500 megahertz. No. We if it exceeds than 1000, okay, 999, we scale them, okay, to be 2.5 gigahertz instead. Okay. Next one. Okay, after you know about the unit, okay, when you read that, okay, everything that you read in the books, okay, will be follow about this SI unit and in this form. Okay. The first, okay, about the chart. One of the most fundamental concepts in the electrical circuit analysis is that of the chart conservation. Although we transfer the charge between different parts of the circuit, we do nothing to change the total amounts of the charge. You can see the charge at a particle, okay, can move from left to right, right to left, okay, but the more charge you move, okay, the more current it is, but you cannot, okay, the charge that flow in the cable, okay, you cannot destroy or create it, okay. We neither create or not destroy the electron when running in the electric circuit, okay. The charge in the motion is represented to be the current, okay. Unit of the charge is coulomb. We use the capital letter when you read that Q is equal to 5 coulomb, okay. We frequently write them in the capital letter because the capital letter is mean are reserved for constant value, okay. And if it used in the lowercase, okay, QT, okay, it means it's lowercase. Letter represent the instantaneous amount of the charge. It means the lowercase is mean the charge will be vary from time to time. When time equal to 1 second, charge may be equal to 10 coulomb. When time equal to 100 seconds, charge may be equal to minus 4 coulomb, something like that. Okay. The next one is a current. Okay. The idea of the transfers of the charge or the charge in the motion is of vital importance to us in study electrical circuits because we may transfer the energy from one point to another. It means the concept of the charge is mean you move the charge from one point to the other, okay, another point, okay. If the charge is moved, it means it generates the current, okay. The idea of them is about here. You can see that if we see the charge will be in the particle, in the blue particle is here, blue dot is here. If one charge is moved, okay, across cross section, okay, in 1 second, is equal to 1 amp. If it have two charge move in 1 second, it means it's equal to 2 amp. Okay. Therefore, the current you can use I, the capital letter and lowercase in the same manner. The capital represent for the constant or the fixed value, and the lowercase is represent for the charge, the current that vary from time to time. Unit of the current is the ampere. Okay, the ampere. The total the charge. Okay, you can write the relationship between the charge and the current will be here. The charge that change in one time, okay, in a certain of time, is give you the current. For example, if you have 1 coulomb, okay, changing or move across the cross section in 1 second is equal to 1 amp. Okay, and vice versa. Okay, if you integrate both sides, you can determine the charge in the form of the current is. Okay, the total charge transfers over all time is that given by this equation 2, and in this case it is convenient to think of the current as the motion of the positive charge, even though it is known that the current flow in the metallic conductor result from the electrons instead. Okay, it means, okay, you in this idea, okay, the charge, you know that the charge is moving, okay, across cross section in 1 second. It means it equal to 1 amp. But in the real world, you know that, okay, the really thing that move is electron, right? The electron, okay? The electron is moved in here. If the number of the electron is moved equal to 1 charge, it means it equal to 1 amp, okay? And the way to define the current in the engineering will be defined by here, okay? The current will be defined completely if you have the arrow direction and the number and the unit clearly, okay? And in this case, if it reverse, okay, the units, the number will be here. Two of them is equal. You can see that the current will be get up equal to 3 amp, but if it revert, it will be minus 3 amp. In the real world, it have the negative current. In fact, it have not, okay? It have not. No minus 3 amp in the real world. But if it have minus, it means the direction that you set, it reverse. In fact, in this case, you can see that the real current must be get up, not get down, equal to 3 amp instead, okay? Two things is the same thing, okay? And if you define them non-completely, it will result in your fail in the exam, okay? If you define only 3 amp in here, you don't write the arrow direction, okay? You're wrong. You write only the arrow direction, but you don't write the quantity of them, you're wrong. You must write the arrow direction and you write the number and the unit clearly. You will present the completely definition of the current is. Next one is the voltage. Can I drink the water a little bit? Yeah. Okay. The voltage, okay. We begin by showing a very general circuit element as the shapeless object, possessing two terminals at which the connections to the other element may be made. There are two paths by which the currents may enter or leave the element. The electrical voltage or a potential difference exists between two terminals, or that there is a voltage across the element. Is unit of the voltage is a volt, is equal to 1 joules per coulomb. You may be defined by the capital V or the lowercase v. The capital V is represent for constant value, and the lowercase v represent for the voltage that vary from time to time, okay? The voltage can exist between a pair of the electrical terminal, whether a current is flowing or not. Okay, we figure draw about the shapeless in here. Okay, it have two terminals. You must define plus and minus in here clearly. Plus and minus and the number and the units of them. Okay, you can see that in this case, it have the minus 5 ohm, 5 volt? No. If it minus 5 volt, it means the plus and minus sign that you set at the first time is must reverse, okay? It must reverse. If it used to be plus, it will be minus. If it used to be minus, it will be plus, and the sign of them will reverse, okay? Two things. The first of, okay, A and B picture is the same thing, okay? It's the same thing, equally, okay? Okay, the next one is here. If plus and minus is 5 volt in here, if you reverse them, give you minus 5, okay, the sign, you must reverse them too, okay? Now, in order to define the voltage clearly, okay, you must write both plus and minus sign and the quantities, the number and the units clearly. Okay, the first one, you define only 5 volt or 10 volt is here, but you don't define plus and minus sign, is incomplete. The second one, you define plus and minus sign, but you don't define the number and the units clearly, wrong. The last one is the correct one. The last one is you define plus and minus clearly, and you define the number and the unit clearly too. You must write them in this form, okay? Because in the near future, you must apply the KCL, KVL, or the Ohm's law, or the other law. You can apply them in the case that you write everything completely. If you write everything incomplete, okay, when you try to use or apply some wrong, okay, it lead you wrong, okay. Next one, the last one is about the power. We have already defined the power and it will be represented by P. We have the capital P and lowercase p in this case. Okay, the capital P is, okay, represent for the power for fixed from time to time, okay, is constantly, okay, such as 10 watt, 20 watt fixed, okay, but lowercase p is represent in the case for vary from time to time. When you define some parameter, you must follow this notation, okay. Next one is the okay, another one topic that the student figure it wrong is to understand and define that the power is absorbed or the power is generated from this device. The absorbed power must be proportional to the both the number of the coulomb transfers power second or the current and the energy needs to transfer 1 coulomb to that element or the voltage. Okay, P equal to IV over here. Okay, but the key is how do you know that the current will be get the power will be absorbed or generated from the power? You check it here. Okay, if the device have two terminal, okay, you define plus minus and the voltage. Okay, you check only in the plus terminal. The plus terminal, if the current get in from plus terminal, the device is absorbed. Remember that. Okay, but if the current get out from plus terminal, it's generate. It's generate. Okay. Yeah, the detail is already in the book. If the current's arrow is directed into the plus mark terminal of the elements, then the power yield the absorbed power. Okay. The negative value indicate that the power actually be generated by the element. Okay. In this case, the same. The power, if the power of them is positive, okay, it's okay. It means it absorbs. But if the powers that you calculate is negative, if it's negative, it means instead the device is absorbed. No, the device is generated instead. Okay. 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 For this, okay, instead we give you the exercise, okay, and checking you it difficult. Okay, I will give you about the example as much as possible and provide you some solution. Okay, you can see, okay, how to solve them, okay, and you will use this technique, okay, to solve about the exercise in the book by yourself. Okay. Okay, in this case, the questions give you the current in this form, right? The current, okay, with respect to time, but it's asked you for, okay, the average value in one period and the chart, okay, the chart. The chart, you know that, okay, the relationship between the current and the chart. If you integrate the current respect to time, give you the chart. But if you differentiate the chart respect to time, give you the current instead, okay? Okay, in this case, the questions give it to you, okay, the current flow in this, okay, the current flow in this, okay, it's asked you to find the average value of them, okay, the average value in one period, okay, one period, you can see that the current will flow periodically, okay, it repeat, okay, every 10 seconds, it repeat one time, okay, one period, okay, and you cut them in one period, okay, you can determine the average of them, okay, the average current by you determines all charge that transfer in 10 seconds, okay, all charge is, yeah, you integrate current respect to time, you integrate any graph, it means you determine the area under this graph. The area under this graph is the thing that we already shading in here, okay? This block, the y of them is 2, the height of them is -4, is here, okay? -4 and 2, okay? It's negatives, okay? And the second block is here. The y of them is 2, the height of them is 2, okay? 2 by 2. The last one, okay? The y of them is 2, the height of them is 6. 6 here, okay? This all in the bracket is only the charge that transfer in 1 second, okay? And all charge that transfer in 10 seconds. You normalize them, divide by 10, give you the average current is 800 milliamp, okay? Next step, okay, if the questions give you in the other graph, okay, you can find the area under this graph and you can find the average current in the same manner, okay? The next one, how much the charge is transferred between 1 to 12 seconds. In 1 to 12 seconds, you integrate only that time, 1 to 12 seconds. Okay, integrate them, give you here. You integrate the clock, give you the area under this clock. Okay, during that time, you can see that this first area and the last area is negative. Only the middle one is positive. Okay, minus 4 multiplied with 1. Okay, minus 4 multiplied with 2. Okay, and the middle is 2 by 2 is here, 2 by 2, and 2 by 6, 2 by 6. Okay, therefore the total charge is about 4 coulomb. Okay, 4 coulomb. Now, in this case, if the questions ask you to plot the chart, okay, in the function from time to time, very easy. Okay, you can check that. Okay, okay. The first one, the chart is 0 because the current is 0. Okay. Next one, when the chart is when the current will be increased, okay, is equal to minus 4 amp. Okay, is negative minus 4 amp. Okay, during 2 time, the total charge is the area of them. The area equal to, okay, the area of this club equal to minus 4 multiplied by 2 give you minus 6 coulomb. Okay, it will be increasing in the linear fashion, and it equal to x minus x, okay, minus x coulomb. Next one, okay, for the second part, the second area is a positive, right? The positive, the charge now is positive. The sign of them is 4 by 4. It means it will be increased by 4 coulomb. Okay, but the overall charge is still negative because it used to reach to the minus x coulomb at this time and increase by 4. Okay, and next one will be increased by 2 by 6 is 12. 12 is here, 12. Therefore, in this step, okay, the final charge in your system is about the x coulomb. And so on. During this time, the charge is constant, no changing. And next time, the charge is reduced again, reduced by another x coulomb, okay, 2 by 4, okay, x coulomb. You can see that it reduced from x to 0, okay, x coulomb. And next one, it will be increased in the same fashion again, okay, increased by 2 by 2 or 4 coulomb, okay, and increased by another 12 coulomb again. Okay. Now, this is a graph that you can plot that. If the questions ask you in the same manner, but the different graph, you can do them in the same way. Okay. The way to integrations or find the area under this graph is the same manner.
John,
okay. Now, we finish the first part of the chapter 2. Okay. We go to the second part. Okay. This now, you know about the basic definition of the current, the charge, the current, the voltage, and the power. Okay, and you know how to find the relationship between the charge and the current clearly by the previous exercise or the example. Okay?
John, can I ask a question? John, I have a question.
Yeah, yes, you can ask.
Can you go back to the problem?
Yes.
Yeah, the Q total first term is minus 4 into 1. In the
Minus
equation.
4, 1 is, yeah.
Shouldn't it be minus 4 into 2, right?
Oh, minus 4 and 2, sorry, minus 4 and 2.
Oh, okay, yeah. Yes. Got it. I got it now. Thank you, John.
Yeah, this minus 4 because the 1, sorry, 1 is here. Because this question asks you between 1 and 12 seconds. You can see that?
Oh, I see.
Therefore, the area is not 8, right? The area is half. It starts from 1. The y of this graph is only 1, right?
Oh, okay.
And the height of them is minus 4. Is here. Okay?
Okay, John. Yes.
Yeah.
Thank you.
Yeah.
But when we draw, we have to draw from 0, right? 0, 0. Start from 0.
Yes, but if the third question is start from 0, you can see that, right?
Question.
Therefore, this is about 8, right? Minus 8. It reaches to minus 8 point here.
I see.
Okay.
Okay. Thank you, Kavija.
You can ask me. Don't worry about that. Okay. One. Can I give me 10 seconds for drinking the water? I talk too much. Sorry. The temperature is considerably cool. Okay. Can we continue?
Yes, John. Yes.
Okay. Okay. In this, yeah, I try to finish the first part. Okay. The first, the first, because we have only maybe less than half of the normal time. Okay. Now the voltage and the current solved. Okay. It is important to differentiate between the physical device itself and the mathematical model which we will use the analysis its behavior in the circuit. The mathematical model is only the approximation. Okay. We will use the expression circuits element to refer to the mathematical model. And for simplicity, we initially consider, sorry. I don't turn off the mobile phone. Okay, I will turn off it first. Okay. Okay, sorry. Okay, is for simplicity, we initially consider the circuit with idealized the component represented by a simple model. Okay, the key is the mathematical model is only approximation, roughly approximate. Sorry. Okay, roughly approximation. Okay, roughly approximation of the physical model. Okay, therefore is far away from the real one. Okay, the key for this, why we must model them, because it's easy for model, it's easy for compute that. At least we know the trend of them. For example, the sort, the voltage sort, the current sort, you already found in the circuit or in the physics lab, but it sorry สอนอยู่เดี๋ยวโทรกลับ sorry สอนอยู่จ้าเดี๋ยวโทรกลับ sorry that okay is my wife is told me that something but I canceled the line already. Okay. Yeah, sorry for that. Okay, I will try to prevent the future problem. Okay, I should turn off the mobile phone, but today I just adding the class and I concerned that almost all of you don't see it yet. Okay, now if you see it's okay. Now the next one, what about the real model and the physical, the mathematical model? The physical model is the real one. For example, the voltage source, such as the battery that you buy in the 7-Eleven. Okay, it's a real model, right? The physics model. But it's different from the mathematical model. The mathematical model is a simple one. In the real model, it maybe have a resistance in the connector. It maybe have the temperature effects, okay? For example, if the battery that you use cannot work well if you use them in a very cool place, okay? But the mathematical model is different. The voltage source, if it generates 10 amp, 10 volt, it generates like that forever. But in the physical model, it's not. Okay. Therefore, in the real world, we always have the problem in this case. If you used to hear about some case that the battery in the Samsung Note 5 years before, you know that if you charge them improperly, it can explode. Okay. This is the physical model. It's not the real model yet. Okay. Now we go to the first one. Every sort that study in the class is only mathematical model, not the real one. Okay, the mathematical models, okay, can represent by here. We use the circle shape to represent independent voltage source because it's a voltage. Therefore, it have plus and it have minus in here, plus and minus in here. Okay, you can see that, and you modify the number and the unit clearly. Okay. This thing is the voltage source, but physically represent for the battery. The battery such as maybe AA, AAA that you buy from the 7-Eleven, or the battery in your car, you see. Okay, we have plus and we have minus in there. Okay, and independent voltage source is characterized by a terminal voltage which is completely independent of the current through it. Okay, and in this case, okay, you can see that some sort, okay, we have subscript S to define them is a source. Okay, the last one is a voltage source, but it's different from the first two because the last one is not the DC source, it's AC. It have the sinusoidal waveform in here. Okay, the symbol F is the subscript S merely identify the voltage at the source voltage and is common, but it's not required. Okay, this thing is called independent source because the voltage that it generates is independent from anything. Okay, it fixed. Okay, and it independent. It depends on itself. Okay, is the independent voltage source is only the ideal source and does not represent exactly any real physical device. It means the real physical device cannot be, okay, cannot work like the voltage source perfectly. Okay. Fortunately, that in this class, everything is only ideal. Okay, the voltage is already here. Okay, and the current. Okay, an independent current source is characterized by the current through the element is completely independent of the voltage across it. Okay, the current symbol is the current symbol is shown in this figure. Okay, the same as the other current definition, you must define the arrow direction clearly and the number and the unit, 10 amp, 5 milliamp, or something like that, very clearly. Okay, the direction is clearly. It's called independent current source because we assume that, okay, the quantity that it generates, how many coamp it generates, is not depend on the other one. Okay, and I would like to tell you one last thing. In the real world, the human cannot create or cannot build the current source. All source in the world is only voltage source. Okay, the nuclear generator, the turbine, the battery, or so on. It's only voltage source. It's only the voltage source. It have no current source created yet. Okay. Okay. We do not know prior what the voltage across the current source will be. It depends entirely on the circuits to which it is connected. You can see that the same as the voltage source. For the current source, you don't know what about the exactly voltage across them. Depend on the load that you connect to them. For example, if this source is equal to 10 amp, okay, 10 amp generate. If you have 1 ohm resistance connect in this code, okay, you can see that the voltage across them equal to V equal to IR. Okay, I equal to 10, I equal to 1, therefore the voltage across them equal to 10 volt. Yes. But if you change the resistance to be 2 ohm, the resistance equal to 2 ohm, what happened? The voltage across them change to be 20 ohm instead. You can see that in this case, the voltage across the source is depend on the load, not depend on the source directly. Okay. Next one, okay, is the dependent source. The dependent source is a very powerful model that frequently used in the semiconductor, such as the transistor and the ICs, very much. Okay, dependent on the controller source, in which the source quality is determined by a voltage or the current existing at some other location in the system being analyzed. A source appears in the equivalent theoretical model for many electronics devices, such as the transistor, operational amplifier or op-amp, and the integrated circuit or IC. Okay, the distinguish between the independent and the dependent is the shape of them. The shape of the dependent is the diamond shape, not the circle. You can see that. And the source is have the first two source is current source, and the second one is the voltage source. Even though it's a current source, but it's not necessarily to depend on the current at some point. It can depend on the voltage. You can see that, but it is the current source. You see only the symbol of them. In this case, it's a current source. Okay, but the first current source, it depends on IX. IX is the current at some point in your circuit. The second one is a Vx. Vx is a voltage across some device, maybe across some resistor in your circuit. Okay. Another two is the voltage source. Okay. 2 voltage source is maybe depend on the voltage at some point or depend on the current at some point. Okay. Now you can see that the dependent source is very important to model semiconductors device. Okay. Use them in the IC. Okay. In the transistor, op-amp, or the other ICs. Okay. Here, to make you a little bit more understand about the dependent source is here. Okay. If your circuit is here, okay, you can see that in this case, this is voltage source, right? It has plus and it has minus in here. But this voltage source, it depends on V2. Where is V2? V2 is here. The voltage across this device, okay? If V2 equal to 3, you can see that you would like to find V output, okay? V load equal to 5 V2, okay? If V2 equal to 3 volt, substitute them in here, you can determine that VL equal to 5 multiplied 3 give you 16, okay? Or in another case, if I told that V2 equal to 10, if V2 equal to 10, what about the VL? VL equal to 5 multiplied 10, give you 50 volt instead, okay? Now, the last one, the interconnection of the two or more simple circuit element from an electrical network. Okay, if the network contains at least one closed path, it is also an electrical circuit. Okay, and okay, you already have the two resistors. Okay, and maybe one or two resistors, one voltage source. Okay, if you don't connect them, it's not circuit yet. You ring them. Okay, you wire welding them. Okay, connect them. It become the circuit already. Okay, the first law that you study is Ohm's law. The Ohm's law is very simple. It states that the voltage across the conducting material is directly proportional to the current flowing to the material itself. Okay, V equal to IR. Unit of V is volt, unit of I is ampere, and the unit of R is ohms. Okay, or you can find I in the term of V and R respectively. Okay. And in this case is here, okay, the symbolize of the resistance is here. Okay, you can check that. Okay, in this case, the current, the resistance is okay, plus in here, minus in here, and the current get in from
Hello?
John, the connection may be lost.
Hello?
Hello?
I think he lost his connection. Yeah. John, we can see you, but we can't hear
okay.
you.
Sorry, the ABAC internet will be cut every 4 hours.
Okay.
Can you hear me?
Yeah.
Okay. I just refresh it. Okay. Sorry for interrupting a little bit. Okay. We came back again. Okay. Can you see this slide?
Yes, John, we can see the slide.
Okay. The Ohm's law. Okay. Be careful about that. Okay. When you apply the Ohm's law, V equal to IR, you multiply plus and minus of V and the direction of the currents correctly. Yeah. You know that in the normally, okay, the resistance is consume the power, right? No resistance in the world can generate the power. Therefore, if it consumes the power, the current must be get in from plus terminal. Get in from plus terminal. Okay. Yeah. If it get out, it means it generate, but it's wrong. Okay. The constant of the proportionality R is called the resistance. The unit of the resistance is ohm. Okay, is the unit of the resistance is the ohm, which is 1 volt per amp, and customarily abbreviated by a capital omega is here. Okay. Okay. The first one will be the first chapter will be clear and wait a minute. Okay. We can go to the next one. Okay. Can you see the new slide?
Yes, yes.
Okay. Now for the chapter 3. Okay. The chapter 3 in this case will be introduce you about the voltage and the current law. Okay. Especially you have in this subject we teach you only 3 laws: Ohm's law, Kirchhoff current law, Kirchhoff voltage law. Only 3 laws. Okay. Only 3 laws. After defining a few new circuits term, we will be ready to begin analyzing a simple circuit constructed from this device. We will apply the Kirchhoff current law, KCL, and we apply Kirchhoff voltage law or KVL. Okay. Okay. We teach you about basic of the nodal, the path, the loop, and the branch. Okay. We concentrate on the Kirchhoff current law and how to apply them correctly. I think everyone, almost every student, know about the Kirchhoff current law, but a few can apply them correctly. Okay, in almost all environment. And the same, the Kirchhoff voltage law. Everyone know that. Okay, the voltage across, okay, in all closed path equal to 0, the sum of them. But the way to apply them correctly is a few. Okay, because you don't define the current and the voltage at each element correctly and clearly. Okay. The next one is about the single loop circuit and the single node pair circuit. Okay. Next is about the series and the parallel connection sort. The resistor, if you have many resistors in the series and in parallel, you have to combine them into a single one. Okay. And if you have the about 1 voltage, okay, you have 2 resistors. How to compute the voltage across each resistor, and how if you have 1 current source, okay, parallel with the resistor, how to compute the current at each resistor part. Okay, this objective of this chapter is to concentrate how to apply KCL and the KVL clearly. Okay, the first one. Okay, the nodes, the path, the loop, and the branch first. Okay, this thing this definition we will use again in the next chapter, the chapter 4, the nodal analysis and the mesh analysis. Okay, we now focus our attention on current voltage relationship in the simplest network of 2 or more circuit elements. The ramp parameters network, and the network is appear as a number of the simple element and a set of the connecting lead. And the distributed parameters network is the network which contains an essentially infinite number of the vanishing small element. The idea of them is the subject will be concentrated on the ramp parameter network. The ramp parameter network is here. Wait a minute. I will show you in some example. Is here, for example. Okay. Concentrate only on, if we concentrate only on, can you see it? Only on this cable. Okay, you can see that this cable, in fact, for example, is copper wire. Okay, it will copper wire. I would like to ask that in this cable, in the real case, where is the resistance? The resistance, in fact, it distributes in every atom, right? Every 5 of them. Not concentrate on the middle one, right? But in order to easy in the computation, okay, we assume that in the entire cable, we have the resistance 10 ohm in here, not distribute in all, because it's difficult to compute. Okay, this thing is called the ramp parameter network. It means if you want to have the cable, you have the 10 ohm. It means it's enough. Okay, but in the real world, you know that the resistance distribute in the cable. Okay. Okay, this is the ramp parameter network. The distributed parameter network we use in the case that you require the more accuracy, but beyond of our subjects. Okay. Now, the next definition is the node. The node is a point at which 2 or more elements have a common connection. Every element have a node at each of its end. It means if you have 2, for example, you have 2 resistors. Okay, if you connect them together, okay, the welding stem, the top and the bottom is become the node. Okay, it becomes the node. Okay, the path is the set of the node and the element that we have passed through. No node will encounter more than one time. Okay, in the circuit, okay, the path it means you go, but you cannot go Okay, you cannot go the same, okay, the same branch again. Okay, it's difficult to count, but okay, the node will be reused again, give you the definition again. Okay, when we apply the nodal analysis, the loop is mean, okay, the closed path, okay, the path is a closed path. If the node at which we start is the same as the node at which end, okay, the branch is a single path in the network composed of one simple element at the node at each end of that element. Okay, now here, for example, this node and this node is the same node or not. The way to checking them is very easy. You checking that any divide between them. If it have no divide, it's only the cable between them. It means the same node. If the same node is mean the voltage at this point equal to the voltage at this point, you can merge them to be the top one. Okay, the top one. Okay, the top and the bottom is the same thing. Okay, now we will go to the first formula, the KCL, the Kirchhoff current law. Okay, the KCL or the Kirchhoff current law is stated that the algebraic sum of the current entering any node is 0. Okay, this law is represent a mathematical statement of the fact that the charge cannot accumulate at the node, and the node is not a current, and the node is not a circuit element, and it certainly cannot store, destroy, or generate the charge. Hence, the current must sum to be 0. Okay, the idea of them is about here. Okay, in this node. Okay, you checking first how many branch connect to them. 1, 2, 3, and 4. Okay, the way to apply KCL is mean the sum of the current will be equal to 0. Okay, but from my suggestion, in the near future, okay, almost all formula frequently used in the current get in equal to current get out. The current get in, how, okay, in this branch, how many current get in branch? 1 and 2. It's have only 2 current get in, IA plus IB. Okay, IA plus IB equal to current get out. Current get out equal to IC plus ID is here. Okay, we frequently in this subject we frequently use current get in equal to current get out. Okay, I will tell you later. So, okay, when we apply the nodal analysis, okay, we frequently use this technique. Okay, easier than you test that. Okay, the sum of the current get out equal to 0 or the sum of the current get in equal to 0. No, current get in equal to current get out. Okay. Okay, next one. Okay, in order to demonstrate you some idea, okay, we give you, okay, this example. Okay, from the circuit shown in these figures, compute the currents through the resistor R3. Resistor R3. If it known that the voltage source supply the current 3 amp. Okay, if it does supply, what about it mean? If the voltage source is here, right? This is the voltage source, this current, okay, this current source, this voltage source supply 3 amp. If it's supply, you know that, okay, the current must be get out from plus terminal. Plus terminal is here, right? If it get out, it will be here. Okay, we show you in here. Okay, that's all. Okay, you can see that if we get out, IR1 equal to 3 amp, right? IR1 equal to 3 amp is get out is here. And this node checking that it is the same node or not. It have no divide between them, therefore it is the same node, right? If it's the same node, you write them in here, okay? And you can apply KCL to them. KCL to them. In this case, how many branch connect to them? It's 1, 2, 3, and 4. Okay, how many current get in? 2 current get in. Okay, 5 amp and 3 ohm. 3 amp is here. Okay, 3 amp is here. Okay, 2 current get out. 2 and I. Okay, in this case, I don't. In fact, I should write that. Okay, I plus 2 amp equal to 3 plus 5. Okay, but in this case, I will use, okay, the sum of the currents. Okay, get out equal to 0. Okay. And you can summarize that, okay, you can formulate the equation, you can state that, okay, I equal to 6 amp, okay, 6 amp. Okay, I use this equation, okay, follow the equation in the textbook that you have in hand. Okay, next one, the Kirchhoff voltage law. Okay, the Kirchhoff voltage law is here. Okay, KVL. The algebraic sum of the voltage around any closed path is 0. Okay, I think from my point of view, okay, the way to apply KVL is a little bit more complicated than KCL. The KCL, you see them like the water. Okay, it means the water get in equal to water get out. Okay, the sum of the current get in equal to the current get out easily. Okay, you only define how many current get in, how many current get out. But the way to define the voltage, you don't know his plus should be here, minus here, or flip them. Okay, the way to define, before you can apply the KVL, you must know how to apply or how to define each voltage value first. Okay, the current is related to the charge flowing to the circuit element, but the voltage is the measurements of the potential energies defined across the element instead. Okay, when we define, before we apply the KVL in the circuit, okay, the first step, okay, in this class, we use them in the clockwise direction first. Clockwise, do you know about the clockwise? Even though almost all is used, okay, the digital clock already, okay, but the clockwise direction is still important, okay. Now, move methodically around the closed path in the clockwise direction, and you define, you write the current. If it have no current defining, okay, you define the current flow in the clockwise direction, okay, and you write down the voltage at each element. If you, okay, if you write them in the clockwise, if it meets the plus, you write in plus. If it meets the minus first, you write the minus, okay. Now, in order to give you more understand, I will show you in the idea to apply the KVL first. In here, in this circuit, we have, okay, in this loop, we have 3 elements, okay, we have plus, we have minus in here, okay. The first step you must, okay, if we can write the voltage across them clearly, okay, V1, V2, V3 here, you write them in the clockwise direction, okay. You can see that for the dy1, you meet minus first, it will be minus V1. You can see that minus V1. Okay. The second element you meet plus is plus V2. The last element, the third element, you meet minus, therefore it will be minus V3. Okay. Equal to 0. Okay. This is about the idea of that. Okay. Now, when we apply in the real case, sometimes you cannot define V1, V2, and V3 clearly. Okay. For example here. Okay. Now, in this case, here, this voltage, you can see them clearly, plus, minus in here, okay, plus, minus in here. But the resistance, you don't know what about plus should be in the top or minus should be in the top, or you don't know what about that. Okay, the first step, you define the clockwise direction. If the questions don't give it to you, you define them in the clockwise current direction too, okay, plus in here. And if the current flow in here, you can see that flow in here. Therefore, the voltage will be plus in here because the resistor is absorb element. It's the absorb energies or absorb the power. The current must be get in from plus terminal. If the current already flow in here, plus must be in this side, and plus side must be in this position, and minus will be in this position. After you write them clearly, you can see that you can apply KVL clearly. KVL is here. 3 must be plus because it meets plus first. Okay. 1 it must be plus because it meets plus first. Vx, okay, it must be plus because it has plus first. Okay, it means KVL can be applied immediately to obtain the Vx. Okay, plus 3 plus 1 plus Vx. Therefore, Vx equal to minus 4. If it equal to minus 4, what happened? In the real case, okay, the real meaning is the voltage that you define the first time will be reverse. Okay, but don't worry, don't change them. Okay, the questions ask you for I, you compute I from the Vx that you get. Okay, from the Ohm's law, V equal to IR, I equal to V divided by R. V equal to minus 4 divided by 10, give you, okay, you can see that in this case, give you minus 400 milliamps. Some of you, when you write the answer, okay, you may be right minus 0.4? No. It's not in the engineering format. If you remember in the previous chapter said that, okay, when you write the number, when you answer every number in the engineering world, write them in between 1 to 999. Okay, yeah, 1 to 999, right? 400 is middle between them. Okay, and you use milliamps instead. Okay. This is only the first two examples, the first two simple questions. Now, in order to give you more understand, okay, we will show you more, okay, show you more example here, okay, to give you more understand, okay. Now, if we have the current flow in here, 5 amp, we would like to find the voltage VX in here. The questions ask you to determine the voltage across that, okay. You know that in this case, about this 2 ohm, about this 4 ohm, you don't know anything. You don't know neither about voltage or the current flow in them, voltage or the current flow in them. Therefore, it's impossible to find Vx in this time. Okay, but in the most right hand, you know the voltage across that. You know the current, you know the resistance. You can find the voltage across them, right? Across 8 ohm. Therefore, this voltage you know, this voltage you know. You can find the voltage across 10 ohm. If you find the voltage across 10 ohm by apply KVL, okay, you can find the current flow into them. After that, you know the current get down, you know the current get in, you can know the current flow in 4 ohm. If you know this current, you can find the voltage. This voltage you know, this voltage you know, you can decrease 2 ohm, okay? And this loop, this completely loop, okay? You can apply KVL, okay? This voltage, you can write them the sum of the 10 ohm voltage and the sum of the 4 ohm voltage equal plus with the sum of the Vx, okay, equal to 0. Now, we start to see about the interesting parameters, okay? The first one is here, okay? Clockwise direction, okay? You know this voltage. You know Vx, okay? Vx, V equal to IR, okay? You know I equal to phi, I equal to X, okay? Phi and X, okay? V10 is about here. V10 equal to here. Now, if you formulate the equations by this, you can see that for the 64 must be plus or minus, must be, you meet minus first, must be minus, okay? And VX is plus in here, minus in here, because you define the current as is B, because you define plus in the left hand, the current flow in here, because the resistance is consume the power, okay? And here, you can get V10. After you get V10 plus in here, minus in here, you can find I10 from Ohm's law, okay? Okay. Okay. You know V10, right? V10, you can find I10. Okay. Write down the appropriate Ohm's law. I10 equal to V10 divided by 10. V10 equal to 20 in the previous step. Okay. You can get 2 amp. The current get down 2 amp. The current get in 5 amp. Therefore, you know that the current get this part equal to 3 amp. Why? Because you can apply the KCL to this node. Okay. To this node. Okay. One current get in, two current get out. Okay. One current get in, the current get in equal to 5 amp, current get out equal to I4 plus with 2. Okay. You can get here equal to 3 amp. Okay. And next step, okay, if you know the, okay, you know the current here equal to 3 amp, you know the voltage across them. You know the voltage across them. Okay. You can see that if we redraw the circuit again, okay, redraw the circuit, okay, we show you only the interesting part. You know the voltage across 10 ohm. You know the voltage across 4 ohm. And for the voltage across V, current start. It's easy to apply when you apply the KVL to this. For the KVL, when you apply them, V10 must be negative because you meet minus first. V4 must be positive because you find plus first. And Vx must be plus, okay, in here. You can guess Vx in this step. You can see that in this example, we will show you when for some case, okay, you must apply KCL and the KVL and the Ohm's law so many times to get the final answer. Okay. Now, the key to correctly analyze the circuit is the first mathematical label or voltage and the current on the diagram. Okay. It means before you apply KCL and the KVL, you must write voltage at each point and the current direction up or down, left or right, clearly at every point first, okay? And after that, you can apply KCL and the KVL will correctly, okay? This way, carefully written the KCL and the KVL equations. We use correctly relationships. Ohm's law can be applied as necessary if more unknown than equations are obtained initially. Okay. Now already introduced about the Kirchhoff current law and the Kirchhoff voltage law clearly. The next step will give you some. Okay. In the textbook will be it don't force you to apply KCL and the KVL in the general circuit immediately. No, it apply them in the very, very easy situation first. Okay, the situation, the first case is the single loop circuit. The circuit, single loop circuit, it means the circuit it have maybe have a several element but a single loop. For the single loop circuit, it means you can apply KCL in the single step and you can determine or you can grab the relationship between the voltage of all elements immediately. Okay. For the single node pair circuit, it means you maybe have 4 or 5 devices connect in the parallel or we have only 2 nodes. Okay. For the 2 nodes, it means you can apply KCL easily. A single KCL equation can link all relationships of all devices. Okay. Now, for my suggestions, after you finish this course, okay, even though you listen the lecture clearly, okay, but you must try to take the exercise by yourself. Okay. The exercise is some of the, at least I think in the practice, some practice problem, it's already have some solution at the end of them. Okay. Okay. But in the problem at the end of the chapters, okay, I think in the internet it already have some internet, I don't know. Okay. It maybe have some, okay, solution to you. But if you're not sure, okay, at least you must try to find, okay, the example that I give it to you or the practice that I give it to you, okay, if you close them, okay, if you close the solution, try to find by yourself, okay, is it match or not, and you will open them, okay, if it match, okay, it's correct one. If it not match, it means it incorrect one, okay. Now, the single loop circuit, okay, we have seen that the repeated use of the KCL and the KVL in the conjunction with the Ohm's law can be applied to the non-trivial circuit containing several loops and the number of the different elements. All of elements in the circuit that carry the same current are said to be connecting in series. The element may be carry equal current and not be in the series instead. For example here, this thing we call them the connect in the series because we have up to 4 devices between them, or 4 devices, right? But all devices will have the same current. Okay, the current flow in this voltage source is the same current flow in this resistor and the same current flow in this voltage source and the same current flow in the R2 resistor, right? All devices will be share the same current. Okay, so if the circuit construct in this shape, we call them a single loop circuit, and it means 4 devices will be connected in the series. Okay, from the series you can see that you can apply the Ohm's the Kirchhoff voltage law immediately. Okay, clockwise direction, right? Vs must be minus because you mean minus first. Okay, R1 is R1 I V across R1 equal to IR1. Okay, and V across R2 equal to VR2. For V2 is plus. Okay, when you apply KVL, you can write them in here. VS1 minus. Okay, VR1 is here. VR2 plus. Okay, VS1 is plus. VR1 is, you can express them in the term of I by apply the Ohm's law. V equal to IR. Okay, for VR2 is the same. VR2 you can express them in the Ohm's law. Okay, V equal to IR again. Okay, substitute them in here. You can extract I in the term of V and in the term of R. Okay. Now, in order to give you more understand, we will give you the example. Okay. Okay. Compute the power absorbed by in each element. Okay. In each element. In this case, the circuit will be constructed here. You can formulate the equations by applying the KVL in the single step. In this case, the questions don't define the current direction. Therefore, you define them to be clockwise direction. if you define them to be clockwise direction, okay, the current flow in the clockwise direction, therefore the current will be get in from plus, get out of plus, therefore the voltage across the 30 ohms plus 1 be in the left hand, minus in the right hand is here, okay. For here, okay, VA, the questions will be defined in this direction, we don't care for that, okay. Now you apply the KVL, okay, from a 120 must be minus because we meet minus first, okay, minus 120, plus V30, okay, plus V30, okay, we meet plus first, plus 2 VA, and here minus VA, okay, and after that, okay, you can see that one equation to unknown. We have V30, we have VA. You cannot solve them, but you can express VA and V30 in the term of I. Okay. In this case, V30, the voltage across them from the Ohm's law, V equal to I and R. Therefore, V30 equal to I 30. Okay, 30 I's. Okay, 30 I's. Okay, and for VA is equal to 15I. No. The I is the reverse direction. You can see that if I go in here, plus will be in the top, but plus in this case, VA define minus in the top. Therefore, it will be negative 15I instead. Okay. After you define them completely, you substitute them V30 in the top equation and VA in the top equation too. Okay. A single equation, a single unknown. Okay. You can solve them and you can find I. Okay. The question is not finished yet because the questions ask you for the power absorbed by this device. Okay. In this case, I equal to 8 amp. I equal to 8 amp is mean the current direction that you define is already correct one. Okay. The current get out, okay, in the clockwise direction equal to 8. Okay. But in this case, if the current get out from plus, it means this device is generate the power, right? But the questions ask you is assume that every device absorb the power. Therefore, this device will be absorbed negative 960 watt instead. It means, in fact, this device will be generated instead. Okay. If you force them to be absorbed, it must be negative. Okay. Be careful about this meaning. Okay. And the second one, the resistance is easy. It's always absorb the power. Okay. Okay. I square R. Okay. Give you here. For here, it's already absorbed, right? Because the current will be get in from plus terminal. Therefore, you determine only 2 VA and determine I, you get P. Okay. Substitute by its side, step by step. Okay. But in this case, VA is substitute them, give you minus. We don't care for that. Okay. And the last one, okay, for the resistor, 15 resistor. Okay. Okay, the resistor 15 ohm. Okay, we go to IR or I square R. We give you here. You can see that, you can check that the sum of the power, okay, generate will be equal to absorb. Okay, the sum of the power equal to 0. Okay, the next one, the single node pair circuit is a period, is a single loop. Okay, single node pair circuit is mean the circuit it have maybe have 4, 5 or 10 elements. We don't care, but all of them connect in parallel. It have only top node and it have only bottom node. Okay, the parallel is mean all of these elements in the circuit have the common voltage across them. You can see that the voltage across this current source, okay, equal to this resistance. The voltage across equal to 30 amps, the current source, and the resistance too. Okay. Therefore, in this case, the questions ask you to determine the voltage, the current, and the power associated with each element in the circuit. Okay. Now, okay. In this case, the top of them is here. We define the voltage across them equal to V. Okay. In the top node, okay, you can see that this node and this node is the same or not? Yes, it have no divide between them. All the top node we have up to 4 bars connect to them. Okay, 4 bars. Yeah, 120 amp. Okay, this, okay, 1 by 30 ohm. Okay, and 30 amp and 1 by 16. Okay, now you can write them, okay, in the term of I1 and I2, okay. In the top of that, you can see that it have 1 current get in, 3 current get out, I1, 30 amp, and I2. You can apply KCL to this step, okay. 1 current get in, 3 current get out, okay. But one equation, 2 unknown, you cannot solve it yet. For generally that, okay, I1, you can express them in the term of V, okay. From Ohm's law, V equal to IR. I equal to V divided by R, okay. Therefore, I1 equal to V divided by 1 by 30, okay. And I2 equal to V divided by 1 by 15, okay. You get here. You simply choose 2 of them, okay. I1 and I2 in the top equation. We provide you a single equation with the single unknown, and you can determine V from this equation. But it's not finished yet because the questions ask you for the detail. It's ask you for the current flow at every point. You know the voltage across them, you can find the current, right? The voltage across them equal to 2 volt, you can find I1 equal to 2 divided by 2 by 30. Okay, give you 60 amp. Okay, I2 equal to 2 volt divided by 1 by 15. Okay, therefore the current I2 equal to 30 amp. The absorbed power in each element again, okay? You know the voltage across them, you know the current flow in them. You can find the power is generated, okay? It's absorbed by here. For resistor, it's easy. The resistor always absorb, okay? You can find P equal to IV or I square R, okay? Or V square divided by R, okay? P, okay, the power at R1, the power at R2. Now the key power is the power in here. The power in here. You can see that in this case, the power plus in the top minus plus in the top, but the current will be get out. If it get out, it means this current source will be generate the power. If it generate the power, it means minus, set them to be negative, okay? Because the questions ask you to absorb the power. Okay, and the last one is here. For the 30 amp is already absorbed, plus in the top, okay, the current get in from plus, therefore this current source always absorb the power. You can see that the sum of power is still equal to 0, okay. Okay, we will reach to this point first, okay. Any question about that?
Ajahn, I have a question. What if we
Okay.
see voltage sources in parallel? How can we solve that?
Sir, hello, Rauri.
Yeah, for example, if we see voltage sources that are connected in parallel with the circuit, how can we?
Which one? This one?
We didn't see it here, but
This?
just an example from real life.
Example?
Yeah, like if we see 2 batteries in parallel, how can we?
The voltage source in the parallel, right?
Yes. Yes.
The voltage source. If you have 2 voltage source, okay, if it's different inside, it cannot be parallel. We will teach you next time. It's here. Wait a minute. This thing, right? Can you see in the slide?
Yes. Yes.
Okay. If you have 2 voltage source, yeah, the first one, you cannot connect them in the parallel, okay? Because when you apply the KVL, it's wrong. Remember that? The voltage source, you can set them to be the parallel if it equal in the side. Okay? 5 amp, 5 volt and 5 volt, yes, you can parallel them. But 5 volt and 10 volt, you cannot parallel them. Because if you parallel, this is for the circuit designing. Okay? Because if you push them in here, one will be try to be charged another one. And make that one will be gone or burn. Okay?
Okay.
Anything?
Thank you, Ajahn. Thank you.
Okay, but the detail will be teach you next lecture. Okay? Not now, because the time is already up. Okay?
Thank you, Ajahn.
Okay, you're welcome. Okay, and one last thing, okay? even though you listen the lecture, is not give you fully understand yet until you try to take the some exercise. Okay, exercise in the book is enough. Okay, you maybe select one of them, not necessarily to do all questions. You do some of them, maybe 20% of the question at the end of each chapter. Okay, to give you more full understand. Okay. Okay, I think the time is up. Okay, now see you next time. Okay. If you don't have any questions, okay, good luck. Dismiss.
See you, Ajahn. Thank you.